Hello everyone, this is Junde Zhang from USW Sydney. Welcome to the postgraduate conference. Today I'm going to talk about the CR structure on nilpotent Lie groups and flat manifolds. So, before really talking about the definitions of the CR structure and some related topic with it, let's first have a look some important conception that we're going to use in this talk. So the first terminology that I want to introduce is called a stratified Lie group. This is a connected and simply connected Lie group whose Lie algebra admits a stratification. So by stratification, I mean that the Lie algebra has a decomposition in a vector space direct sum, so that the first linear subspace N1 actually generates all the linear subspaces by the Lie bracket. So for example, we have the linear subspace N2 equal to the Lie bracket of N1, N1, and N3 equal to the Lie bracket of N1, N2, and so on. And we also call the first linear subspace N1 as the horizontal distribution. And we will talk about this a lot in this talk. So we actually will have a look at a real stratified Lie group that carries a complex horizontal distribution. And we also want to have a look the mapping that preserve this complex horizontal distribution between two real stratified Lie groups. And because we want to make a real linear subspace or a real manifold into complex manifold, so the next terminology that I want to introduce is called a complex structure. So with this complex structure, we can actually define a complex manifold in an algebraic way. So geometrically, a complex manifold can be defined as a topological space which is locally equivalent to a neighborhood of Cn. And we have a lot of examples for the complex manifold. For instance, we got Cn itself is a complex manifold, and we also have a complex projective plane or complex projective space, and also the Riemann sphere. So algebraically, we can actually define almost complete. We can actually define complex structure via a conception which is called almost complete structure. So, given a real, given a even dimensional real manifold, for any point in that manifold, we can define a linear isomorphism from its tangent space to its tangent space, so that the square of this linear map is equal to the negative identity. And we also notice that this linear isomorphism is actually very smoothly on entire tangent space. So we can actually extend this definition into the tangent bundle, so that almost complete structure defines on entire on tangent bundle is a tensor field, and almost complex and a real manifold admits this structure. This almost complex structure is called an almost complex manifold, but notice that this almost complex manifold is not yet a complex manifold. For example, we got a six-dimensional sphere S6, which is admit almost complex structure, but is not a complex manifold. So, in order to make almost complex structure become a complex structure, we need to use following theory, which is called the Nuremberg theory. And this theory actually states a necessary and sufficient condition so that an almost complex structure is a complex structure. By doing so, we need to introduce a new type of tensor, which is called the Nugent-Haus tensor. This tensor is formulated by relations of Lie brackets and also the almost complete structure defined on the section of the tangent bundle. And the condition so that an almost complete structure to be a complete structure is that the Nugent-Haus is equal to the Nugent-Haus tensor actually vanished on the section of the tangent bundle. And we're going to use this Nugent-Haus tensor, the conception of the Nugent-Haus tensor, and the Nuremberg theory a lot in the following examples. So, with those definitions and terminologies, we can actually give an abstract definition for the CR structure and CR manifolds. So let's first have a look at the definition of CR structures. Let M be a real dimensional. Let M be a m-dimensional real manifold, and T10M is actually the subbundle of the complex of the complexification of the tangent bundle. So T10M is actually the complex subbundle, and also this T10M has a complex rank n. So if this complex subbundle is a CR structure, it has to be satisfy. It has to satisfy the following conditions. The first one is the intersection between T10M and its complex conjugate is actually equal to 0 element. And the second condition is this complex subbundle is actually integrable. So with with the definition of CR structure, let's then have a look at the definition of the CR manifold. So that T10M is actually a CR structure, and we call the pair assume manifold M and a CR structure is an abstract CR manifold of type NK, and N here is actually the complex rank of CR structure, and we also call it as a CR dimension, and K here is actually the CR codimension, which is given by the dimension of real manifold M minus the real dimension of CR structure, which is 2n. And in particularly, suppose that M is a submanifold of a complex Euclidean space, and also the CR structure is then given by the holomorphic tangent vector fields on Cn intersect with the complexification of tangent bundle, and in this case we call this pair as an embedded CR manifold of type Nk. And also in the CR geometry, there's a very interesting question that is to find relation or mapping between an abstract CR manifold and an embedded CR manifold, and to find the condition so that this mapping is an isomorphism or a diffeomorphism, and we will show this in the following example later. So let's then have a look how those definitions works on a particular example. So suppose that n equal to k, suppose that m equals to n as a real stratified V group, and M10 is actually a complex subalgebra, so that this M10 intersect with this complex conjugate is 0 element, so that the first condition of CR structure is actually satisfied. And then we also define a horizontal distribution equal to the real part of the direct sum of M10 and its complex conjugate, and then define an almost complete structure from N1 on horizontal distribution. And because we want this complex subalgebra is a CR structure, in other words, we want the horizontal distribution can be complexified. So this is equivalent to almost complete structure. JE is actually uncomplex structure, and by the Newlander-Berger theory, we have the Nugent-Hauss tensor must be vanished on the horizontal distribution. So we have this condition, so that the complex subalgebra M10 is a CR structure, and then a real stratified V group with this CR structure is called a CR stratified V group. And with this definition, we will see some particular examples. So the first one is called Heisenberg group. We can identify this Heisenberg group as a real Euclidean space R2 plus 1, also with coordinate Zt, where Z belongs to Cn and T is just a real number. And we also choose a holomorphic tangent vector field equal to the half xj minus iyj, where xj, yj spans the real tangent vector field, which spans the entire horizontal distribution. So we can see that this holomorphic tangent vector field is not equal to its complex conjugate, so the first condition is automatically satisfied. And the last thing is we want to show that this horizontal distribution can be complexified, and then we define an almost complex structure, which is mapping xj to yj and yj to minus xj for all j from 1 to n. So in this case, by simple calculation, and we can actually calculate that the Nugent-Hauss tensor is actually equal to 0. And in another word, this almost complete structure is a complete structure, and the horizontal distribution can be complexified. And the Heisenberg group is an abstract CR manifold of type N1, and we also call and if the horizontal if the CR codimension is 1, and we call this type of CR manifold is hypersurface type, and hence Heisenberg group is an abstract CR hypersurface. And also there are different examples for the CR hypersurface. For instance, we got S2n plus 1. This is odd-dimensional sphere. This is a CR hypersurface, and it's actually the family of CR hypersurface. And we also, for the embedded case, we got the boundary of the single domain, which is defined like this. And this is a submanifold of Cn plus 1. And in the last example, we will see that there are CR equivalents between those CR hypersurface. So let's move on to the next example, which is the Andrew group. This is a real four-dimensional Lie group with step 3 stratification, which means its Lie algebra equal to n1, n2, n3. So the left invariant vector fields are given by x1, x2, y, and z, and the horizontal distribution is given by x1, x2. So the Lie bracket relation for those four vectors is actually the Lie bracket of x1, x2 equal to y. So the second layer n2 has only one dimension, and we want to show that this horizontal distribution can be complexified. So we choose an almost complete structure defined by x1 mapping to x2 and x2 mapping to minus x1. And also by simple calculation, we can see that Nugent-Hauss tensor is equal to 0 on the horizontal distribution like this. So this horizontal distribution can be complexified, and we said that the Andrew group is a CR manifold of type 1, 2. So for the corresponding embedded CR manifold of type 1, 2, we have the cubic form is given by like this. This cubic form is a submanifold of these three, and also there are a lot of further properties for the cubic form, but we will not talk about here. So let's move on to the final example, which is CR equivalence on CR hypersurface. This theory basically states that the following mappings are actually CR isomorphism. That is, phi, this little phi here, and f are CR isomorphism. So by CR isomorphism is a mapping. It is actually a diffeomorphism mapping that preserve from two CR manifolds of same type that preserve the horizontal distribution and also commute with the complex structure. So we want to conclude this theory. We want to show that this f and this little phi are actually CR isomorphism. So notice that this boundary of single domain is actually an embedded CR manifold, and we can actually find the coordinate and to write down the tangent vector fields. And we also know that the Heisenberg group H is already with the coordinate. So we can actually write down a well-defined mapping and to calculate the push forward of this mapping to conclude this F is a CR isomorphism. And for this little phi, we do the same thing, but we need to use a Cayley transform. We need to use the Cayley transform. So in the following lemma, this lemma tells you the Cayley transform is actually a biholomorphic mapping that from a unit ball in Cn plus 1 to the single domain. Then by restricting to the boundary of the unit ball minus a point, and we can have a boundary map of this capital phi is exactly this little phi here, from the boundary from the odd-dimensional sphere 2n plus 1 minus a point to the boundary of single domain. So in other words, we just need to calculate the push forward of this capital phi, so that each holomorphic tangent vector field in S2n plus 1 is actually equal, by acting of this push forward, is equal to the holomorphic tangent vector field in the boundary of single domain. So we can conclude this theory. And then from this theory, we actually have following observations. So the first one is that because we already know that the odd-dimensional sphere S2n plus 1 admits a CR structure, and we also know that this phi prime here is actually a CR isomorphism because the composition of two CR isomorphism gives a CR isomorphism. So, in other words, the CR structure in S2n plus 1 is actually preserved to a one-point compactification of the Heisenberg group. So this is the first observation, and then the second one is because we know that an odd-dimensional sphere can be viewed as a homogeneous space, and in this case we choose the homogeneous space as the special unitary group quotient by its Borel subgroup via this identification, and we also know that the Heisenberg group is actually a maximum nilpotent subgroup of SUn plus 1, 1. And then we can define a CR map from the Heisenberg group to the homogeneous space J mod B, so that the CR structure of Heisenberg group is actually preserved in the homogeneous space J mod B. And by those two observations, we can actually conclude our research questions. So the first one is, given J is a real semi-simple Lie group, and B is Borel subgroup, and so that J mod B is actually a real flag manifold. And N is actually a Iwasawa nilpotent subgroup of J admits a CR structure. And the omega here is actually the embedded CR manifold with the same type of N. And we want to show that the following sequence is actually formed by CR mapping. In other words, this mapping F and little phi here are both CR maps. So for example, we have N equal to E as an Andrew group, and in the second example, we know that the cubic form gives a CR isomorphism from the cubic form actually gives a CR isomorphism to the Andrew group. So this F here is a CR isomorphism. And we also know that the Andrew group is actually nilpotent subgroup, a maximum nilpotent subgroup of a real symplectic group SP2R. And SP2R quotient by its Borel subgroup is called a Lagrange. It can be identified to a Lagrange flag manifold. So we want to find a global CR homomorphism between Andrew group to Lagrange flag manifold. And we also notice that by Bruchheit decomposition, J mod B is actually the disjoint union of the N orbits, and N here, and the Iwasawa nilpotent subgroup is actually the open and dense subset of J mod B. And also, J mod B is actually a compactification of N. So in other words, what we really want to show is the CR structure on N can be preserved by a compactification like this. So this is the first question. And the second one is given a real stratified Lie group. So under what conditions there does exist or not exist or doesn't exist a conflict structure defined on the horizontal distribution, so that N admits no CR structure or N admits a CR structure. So for example, if J as a real semi-simple Lie group given by SL5R, which is a special linear group, and N is a nilpotent, is a maximum nilpotent Iwasawa subgroup. And we know that the horizontal distribution of this N has dimension 4 because SL5R has only 4 simple roots, and the second layer has a dimension 3. So in this case, we cannot find an integrable almost complete structure defined on horizontal distribution. In other words, there's no complex structure defined on horizontal distribution, so that this N is a CR manifold, and we want to find more conditions like this, and to conclude under what condition there's no CR structure. So that's all for my talk. and thank you for your listening.